All right, this first one here, this is 500 liters of water and 7 ppm. How many grams of lead are actually here? So this, the parts per million, parts per billion stuff, these were basically mass divided by mass problems multiplied by a factor. So the percent ones you multiply by 100, and then the parts per million one you obviously multiply by a million. The parts per billion one you multiply by a billion. So what we need is we've got a mass of solute, and we need a mass of solution, and we're going to multiply this by a million, and then the number here works out to be 7 parts per million. So what are we looking for in this problem? Grams of the solute, correct? Okay, so do we have the mass of the solution number? No, but we kind of do. How do we kind of have it? A liter of water is a kilogram. So water's density is 1, right? So one gram per milliliter. So if you've got a liter, then you've got a kilogram, because a liter is 1,000 milliliters. And so if 1 milliliter is 1 gram, then 1,000 grams is a kilogram. So this would be 500 kilograms, or 500,000 grams. So we'll use that 500,000 grams number. So I got this mass of the solute, so this is 500,000 grams. Actually, of solution. And so when I rearrange this, I get mass of solute is equal to 7 parts per million times 500,000 grams divided by 10 to the 6th. And what's that work out to be? Mm-hmm. 3.5 grams lead. Okay, so 1 sig fig, so 4 grams of lead. Is that a lot? 4 grams? No, it's not very much, but that's actually the limit. That's 7 parts per million. So the 7 grams might not seem, or sorry, the 4 grams might not seem like a lot, but your body can't really get rid of it once it's inside of you. So what's the issue with lead poisoning in water? Is it acute or cumulative? The issue. Cumulative. Acute would mean I got so much lead in my water that I drank it and I died, like right then and there. This is, I drink it and then it builds up in my body over time, and then it causes either nerve problems or cancerous problems. So the 7 parts per million, even though this doesn't seem like a lot, I mean 500 liters of water, how long would that take you to drink? No, about 4 liters is a gallon. Here's a liter. So 500 of these, not that long. I mean, 6 months. Yeah. So if you're getting 4 grams of lead, you could be getting 8, maybe 10 grams of lead a year, and that just doesn't leave your body. That's the problem with it. Okay, how about this next one about best electrolyte, worst electrolyte? So which one's let's go with what's the worst electrolyte? This one here is definitely the worst, so I'll write that number 4. Why is it the worst electrolyte? It's not soluble, so it's not going to give you anything. Its numbers for electrolyte number is 0. It will not split into any pieces. So putting this into water wouldn't cause it to transfer electrons through electricity in any way. So what's the best one? The calcium chloride is the best one because it gives you, this guy here gives you 3 pieces, right? And then what about the sodium bromide and the potassium nitrate? they're the same. They're tied. They both give you 2 pieces. So you, let's do this. So 3 parts, 2 parts, 0 parts. So there's my 0 part, there's my 3 parts, and then those are my 2 parts. So if you put either one of those into water, with the same amount, you get the same electrolytic effect. Hopefully nobody tried to break up the nitrate into its components, the nitrogen and the oxygens, because it's a polyatomic ion, so it's stable, so that's not going to happen.
Does the rules of solubility come in if they tie at all?
Yeah, it doesn't matter.
What about their charges? Like, because they're both plus negative.
What would be the other option?
Like I think their oxidative number or something.
The oxidation number is +1 and -1 on them?
Yeah, like would you look at that? Because if I just before, like if we just didn't have these nodes or something, then I would think they're both 2 parts, but then would you go to the next step to find?
They're both +1 and -1.
But if like one, let's say, was like +2.
Sure, if it was like...
then would that make that one like the second one or the third best?
If it was... can you even be in that situation? Yeah, magnesium sulfate, sure. Yeah. Sure, if the charge was +2, it broke into 2 pieces, then yeah. So if like Epsom salt was the thing up here, then the 2 pieces that it broke up into would be both +2 and -2, versus these 2 are both +1 and -1, and then that one would definitely be better because it's got double the charge. Give 2 reasons why chemical reactions occur. Okay, so what's going on? What's nature trying to do? Yeah.
Disorder.
Lose
energy.
So increase my S and decrease my H. All right. So this diamonds are forever. What's wrong with this? They're not. The carbon that's in the crystal structure will eventually break down to a carbon that's in the graphite structure, and that will eventually break down into carbon that's in the solid structure, which is just charcoal. It just takes a really long time. But is the universe thinking about that, taking a long time? It's quadrillions of years old, so the time that it takes for this to happen is super fast as far as it's concerned. Entropy. Okay, so what does this measure? Its symbol is an S, and it's kilojoules per mole Kelvin. It doesn't have to be kilojoules per mole Kelvin. It has to be moles in Kelvin, but it could be any energy unit. It could be kilojoules, or it could be joules, or it could be BTUs. Not that anybody would ever use that, but energy unit. And then the enthalpy, what does this measure? Say it? Just measures the energy of a system. And it's H, and it's just kilojoules per mole. And Gibbs free energy, what is that? What's the usefulness of the Gibbs free energy?
So we were kind of talking about, like, the free energy is the energy that you don't have to, like, constantly put energy into. It just kind of happens. Yeah.
It's if it's spontaneous or not, the spontaneity of a reaction. So It's G, and it's also kilojoules per mole. So when we say spontaneity of a reaction, we mean, is the reaction going to happen by itself, or do you need to put energy into the reaction to get it to happen? Give an example of an endothermic. A given reaction is endothermic and becomes more ordered. Is this spontaneous or non-spontaneous? Okay, so what's endothermic mean? Yeah, the endo is like our skeleton is an endoskeleton. It's inside of our bodies, and an ants is an exoskeleton. So this would be thermic, meaning energy. So energy brought into the system, and it becomes more ordered. So definitely non-spontaneous, and no time will it ever be spontaneous. It's gaining H and it's losing S. So those are the two things that nature doesn't want to happen. So definitely an energy intensive thing. Okay. When you look at this problem, we need to think about this equation here. The delta G is equal to delta H minus T delta S. And when I'm reading this, there's two things that I need to pick out of the pieces of information that I'm given. So what's important to recognize?
Kilojoules, kilojoules.
I've got kilojoules and joules, so I can't do any subtraction between the two terms unless their units are the same. So I need to either convert the joules into kilojoules or the kilojoules into joules. I think it's easier to convert the kilojoules into joules. I just move the decimal place over 3 spots, and this becomes 4,100 joules per mole. You could have gone the other way with that, but it would be 0.012 kilojoules per mole for the entropy. And then one other thing.
Celsius and Kelvin.
Yeah, this is in Celsius and it has to be in Kelvin. So 273 here, so 292 K. All right, so I've got 4,100 joules per mole, and I'm subtract off 292 K times 12 joules per mole Kelvin. And so then my kelvins cancel out, and I get 4,100 minus 292 times 12, and I get 596 joules per mole. So is this spontaneous or non-spontaneous? This one's non. Okay. All right, and then what about at 78? So we'll go 273 here, and we'll go 192, and we'll go K, and we'll do this calculation again. And 291. Did I mess that up?
Yeah.
Thanks. Oh yeah, I totally messed that up. All right. $351. Yeah, that's better. I wrote the same number down. So I get negative 112 joules per mole. So spontaneous. So all this person did to change the spontaneity of this reaction is change the temperature, and that's definitely something that a chemist would do to try to get some sort of process to happen, or maybe you don't want it to happen, but simple temperature change can make the reaction occur. Explain how you'd make 500 milliliters of 1.25 solution of sodium hydrogen carbonate given solid sodium hydrogen carbonate. Okay, so what do we need to do first?
Get the right mass amount for the sodium hydrogen carbonate.
Okay, so I want it to be 1.25 moles per liter, and I've got a half a liter, and I need 1 mole to, what is baking soda's number? 22.9898 plus 12.011 plus 1.0795 plus 15.9994 times 3 equals, is it 84? Divided by 2 times 1.25 equals, so 52 point, cool. 52.6 grams. Alrighty, so we got this, and now what are we gonna do?
Now you put that in your volumetric class.
Okay, so add my 52.6 grams of sodium bicarbonate. To a 500 milliliter vol flask. And then, what are we gonna do next?
Add partly with water.
Okay, I'll
Just
say
enough to get it to
like
dissolve.
3/4 fill H2O and mix. Then fill near line. Fill 2 line with a dropper. Okay.